First talk is a constant factor approximation algorithm for the asymmetric traveling salesman problem. This was received best paper award by Ula Svensson, Jakub Tarnowski, and Laszlo Veg. And I apologize for any mispronunciations therein. Let's go ahead and get started. Each of the talks will be a half hour. We'll be leaving a few minutes for questions at the end of each talk. Thank you.
All right, thanks for the introduction. Everybody can hear well? Okay, good. So thank you very much. It's an honor to be here giving this talk. This is joint work with Ula Svensson. We are at the EPFL, and with Laszlo Veg, who is at the London School of Economics. Okay, so the traveling salesman problem is the problem of given n cities and distances between them, finding a shortest tour that visits all of these cities. Maybe like this. Okay. So this is a well-known problem. It has been studied already in the 19th century by Hamilton and Kirkman. You probably know the term Hamiltonian paths, right? It's a benchmark problem in computer science. It's one of the most studied anti-hard optimization problems. However, our understanding of it is quite incomplete when it comes to approximation algorithms, which will be the focus of this talk. Okay, so we want to understand what we can accomplish with efficient computation, probably. Okay. So our focus is approximation algorithms, and there are two basic versions of the problem. The first is the symmetric version, where the distances between every pair of vertices are the same in either direction. Okay, so here it's quite easy to get a two approximation algorithm, and there is the celebrated result by Christopidis from 40 years ago. Who got a 1.5 approximation. This is taught in undergrad courses, and this is still not improved. It's a huge open problem to improve it. Okay? So we're interested in the asymmetric version, where we do not have this symmetricity assumption. So for example, this is Mont Blanc, and maybe it's really expensive to get on top, but if you believe this picture, then you can fly right off of it. Really cheap. Okay. Some facts. Alright, so we focus on this one. So formally we're given an adjointed directed graph, and we want to output a minimum weight tour that visits each vertex at least once. Okay, so maybe the graph looks like this. There are some weights and edges. You can see they are not symmetric at all. And an example tour might look like this. Okay, so you might notice that some vertices have been visited more than once. Equivalently, there is the version where you could say, okay, I want each vertex to be visited exactly once, but then you need to have a complete graph with the triangle inequality on the weights. Now, we prefer this version. Okay, just a graph and at least once. Okay, so there's another formulation in which we say, okay, we want a minimum weight connected Eulerian multigraph. Okay, so Eulerian here means that for every vertex, the in degree should be equal to the out degree. So we like this formulation because, well, first of all, one reason is that this brings us to the standard on P. And also, if you just give me such a minimum weight connected Eulerian multigraph, I can easily order the edges so that I get some two. Okay, so this really is the same thing. So this brings us to this LP called the held curve relaxation, where we have a variable XUV. So the number of times that you traverse an edge from U to V, and you want to minimize the total weight of your tour, subject to two constraints. First is this Eulerian constraint. Okay, so this notation means that fractionally the in degree should be equal to the out degree. Second, if you just have that, then you might find that your solution contains subtours, which look like this in the picture. We don't want that, so we have this other family of constraints, which is called the subtour elimination constraints. And here it says that for every set of vertices, at least 2 units of flow should be entering and leaving at this set. Okay? If you have seen this in your program in the past, you might have seen it in the version where you have at least 1 unit of flow leaving a set. We prefer this version because it's a bit more symmetric. Leaving and entering together should be at least 2 units. Okay, this is the LP, and Again, we are really interested in the question of what is the integrality gap of this LP. Okay, so people want to understand, like, okay, there are some various algorithms, but how good is this particular algorithm, or just solve the LP? Okay, how good is this? All right, so once the minimum weight connected O'Leary multigraph. And well, there are two natural approaches, and they consist in relaxing one of the two conditions. Okay, so maybe you want to begin with something that's not connected, or maybe you want to begin with something that's not O'Leary, and then work your way to the other constraint. Okay, so now in the first line of thought, there is the very nice, elegant log n approximation by Flisgelgat and Mattioli from 1982. I will actually show you this algorithm later. So this is based on repeatedly finding cyclic covers and adding them to your solution. And this people thought on how to improve this, and 20 years later, Blazer did so to get a 0.99 log n approximation. Okay, so an improvement in the constant in front of the log n. And now the world record in improving this particular approach stands at 2/3 log n by phi n sig. Yeah. So the other approach is to first find the spanning tree and then worry about making your solution Eulerian. So here we have this very influential work by Asatful, Gemans, Mondri, Olis-Garan, and Saveri, who gave a log n over log n approximation via the so-called twin trees. So this is the first first asymptotic improvement in over 20 years. And then Olis-Garan and Saveri used the same approach to get a constant factor for planar and for bounded genus graphs. And another Olis-Garan showed that the integrality gap of the LP is actually, at most polylog n. So here this is an exponential improvement. Unfortunately, it's not constructive. They go to a solution of the Candyson-Singer problem. In terms of hardness, it is known that it's anti-hard approximating is within the factor of the form 1 plus epsilon, essentially. And it's also known that the integrality gap of the LP is at least 2. Okay? So if someone says that ATSP is too hard, then they might be referring to this. Okay, so there is a big gap in what we understand about LP, and an even bigger gap in the approximation ratios that we think are possible. All right. So then a new approach, which I put on the left because it also relies on keeping the graph Eulerian, was introduced in the work of Ulla Svensson, who in 2015 introduced a new easier problem called local connectivity ATSP, and showed a reduction from getting a constant factor approximation for ATSP to solving that problem. And then that problem was solved for unweighted graphs, and that gets to a constant factor approximation for unweighted graphs. Okay. So on the left you have a lot of great people trying for 30 years to improve this approach. Here, right. On the right, we have also lots of strong researchers putting a lot of effort into improving this. Here, though, there's just one guy. No, jokes aside, this really looked promising to be maybe even low-hanging fruit, perhaps, because you see. The solution of this local connectivity as easier problem for unweighted graphs was actually really quite easy. The other parts of the paper are the real deal. And so we thought, okay, let's just try to make that part more general, more complicated. So we tried and we could do it for graphs that have two different edge weights. Okay. So that's the history, and now we can get a constant factor approximation for the general ATSP. And this is with respect to the health calculation. So on a high level, the highest of levels, the difference between the previous paper and this one is that for the two edge weights, we just reduced using census reduction to solving local connectivity ATSP on graphs that 2 edge weights, and then we could solve this. Okay. Of course, we tried this for general ATSP, and you can use the reduction, and then you could not solve it. In fact, we even couldn't do it for graphs that have 3 different edge weights. It was getting way too complicated. So instead, we use a different path. We actually reduce the problems, thinking the realm of ATSP, to more structured instances. So we proceed by this series of reductions. Really structured instances, okay? Until finally there is enough structure using this reduction by Spencer, we can solve the problem using a somewhat similar approach. Okay? So this is the map of our proofs, and I will show you a short tour of this part. Okay? Maybe not the shortest tour, but it won't be too long. Okay, so I will show you 2 major ideas that we have, that we use. So the first is that, okay, you're given edge weights that are totally general, totally arbitrary, and this is somehow why ATSP in general is hard. So in fact, we show that for free you can get weight functions that are not arbitrary, but they come from certain laminar structure of sets. Okay, I will explain this in a minute. And then the second big idea that I will show you today is that we can make progress by recursing. So you can freely, not freely, but you can recurse as long as your LP value drops when you recurse. Okay. Just some points that I will make clear later also. Okay. So the first thing will be a reduction to what we call laminarly weighted instances. And the word laminarly is indeed not valid for Scramble. So this proceeds via LP duality. So the health car relaxation has a dual, which has a variable ys for every cut s in the graph, and to maximize the sum of all these variables times 2. Okay, so a solution might look like this. You have some sets of vertices, and then you have some values associated with these sets. There are these red numbers. Okay, there are some constraints, of course, but I don't want to get into details. Essentially, by using complementary distractions and time crossing, and doing some rewriting, simplifying, you can get the following structure. Okay, so you get the graph, and you get the primal and the dual solution, and the dual solution looks really like in the picture. Okay, so it's supported on a laminar family of tight sets. The laminar family means that it really looks so nicely, so there are no 2 sets that intersect non-trivially. Okay? And tight means that the LP tells us, okay, you should probably visit this set once, at least if you wanted the 1 approximation. And the weights are not arbitrary. I mean, you will notice maybe that this tuple does not have the weight function. It's because the weights are actually given by your dual solution in the following way. The weight of every edge is the sum of the dual values associated with the sets that this edge crosses. Okay, so here, for example, you have 2 plus 5 plus 1 for this edge. Or for this edge, you have 1 plus 3 plus 2 plus 5. Good math. Okay. And in the other direction, if you happen to have an edge in the other direction, then its weight is the same. Okay, so it's a bit symmetric this way. The graph is not complete, but if you have edges both ways, that's the case. Okay, so we show that if you have a raw approximation algorithm for these laminarly weighted instances, then for free you get a raw approximation algorithm for general instances. Okay, so you really can assume that your instance is such. Okay. One more thing, the health curve lower bound is the primal optimum, which is equal to the dual optimum, and the dual optimum was 2 times the sum of all these values. Good. I will show you the main thing in the talk today will be a reduction to what we call irreducible instances. Okay, and the basic idea here is that you can recursively solve smaller instances using the same algorithm. And that's not dangerous as long as the optimum drops if you recurse. But if it doesn't drop, then our instance will look like this. It will have some long path. So let's take a detour and let's do it so that I can show in a simplified setting why it makes sense to why it's not dangerous to recurse if the optimal drops. Okay? So actually, let's look at this algorithm by Feliz-Galbiati Mathieu. Okay? We want to find the minimum cost cycle cover to begin with. So we find one. Okay? And the cost of this cycle cover is at most opt, because after all, opt is the cycle cover, consisting of just one cycle. And then we contract. Here by contract, actually, I mean that we choose one representative vertex from each cycle and induce on that. Okay, so now we find another mean cost cycle cover. Again, this is bounded by opt. Again, we contract and induce and repeat. And we type 3 times opt. And now the graph is connected. This is approved. Good. Okay, the worst case is that all the cycles have length 2, so we'll need to repeat this log n times, because download axis decreases 2 times each time. Okay, so this is a log n approximation. However, it's really pessimistic. Like, do we find if the value just dropped when we reduce on this smaller instance? So we do make some progress after all, right? So what if the value of opt would drop by, let's say, a factor 9/10 each time? Well, then you would get this nice geometric series that just converges to some constant time. Okay? Awesome. So, well, no one has been able to pursue this strategy with the cycle cover approach, and people have tried. But we pursue it using the structure of this laminar structure that we have. Okay. Now let it go. And okay, just a reminder of what we have. The structure that we have is that the weight of every edge is the sum of the dual values that this edge crosses. Okay. So our key idea is that we're going to recurse by contracting the laminar sets, the sets in our laminar family. Okay, so let's say that we want to contract this large set, and it has these boundary edges. Okay, good. So it's pretty easy to see what to do with the graph, and this is a laminar family, so it all just shrinks very nicely. It's only not so clear what you should put as the new dual value associated with this new vertex set. Okay, so bear with me. I will motivate how to choose this. Okay, so what we're going to want to do is to lift a tour in the contracted instance. Okay, so we have contracted this. Now we call our algorithm recursively. It will find us a tour. Okay, now we want to lift it back. Okay, so we will trace the movements of it like this. Okay, so we start. Okay, let's trace it. Okay, we have traced so far, but now there is a hole in the middle. This is not a lira, not good at all. We have to do something. So we do the intuitive thing. We just put the shortest path. Okay, this. Okay, now we can continue tracing here. So we trace. And now we have to, again, add the shortest path. Okay, now this is Euler. Very good. And this number we set so that we can always pay for this URI. Okay, of course, this costs something, and so we want to be able to afford this. Okay, so this will be set to the maximum cost over all the possible ways to enter and exit. Okay, because when you're lifting from this, you don't know in which vertex you're entering and leaving from. So you have to have this pessimistic path. Okay, so if this is in fact the maximum cost of the shortest path from this green guy to this green guy, then in this example the cost is 5 plus 2 plus 2 plus 1, 4, 3, okay, 17. Okay, so we will put 17 in here. And this is really the worst case. Here the path crosses every tight set. Okay, it can't be any worse. That's something that's easy to prove. So the contraction has not increased the LP value because we got rid of all these sets that had these values, and now we replace this with their sum. But maybe this is smaller. Okay. So if this is in fact substantially smaller, then we say that S is reducible. Okay, this set is reducible if when I contract it, the LP value drops a lot. Okay. Okay, so let's review what we have done. the lift is not more expensive than the tour in the contracted instance because we have put this 17 essentially to pay whatever happens here. So that's fine. That's by design. Are we done? Well, unfortunately, we're not quite done yet because this lift is a subtour, but maybe it's not a tour. You probably can see that there are some unvisited vertices inside. Outside, everything is visited because that was a tour in this instance on the right, but we are not done yet. So let's say that this set is reducible, okay? That the contraction does decrease the LP value a lot. Then we can actually use this remaining budget to complete this lift into a tour. Okay? So let me show you how to implement this. Okay? So this will be the algorithm if there is a reducible set. Then we select such a set, we contract it, okay? And now you see it's 14. So now we are assuming that actually the LP value has dropped. Okay? Good. So now we recursively find some tour. And, okay, so this is the tour. And the cost of it, well, the LP value here was opt on the left. On the right, it is opt minus some substantial drop. In our case, it's 3. Okay? So this gives us some budget to actually patch up this instance. Okay? So now we lift. And, okay, we have our lift. This is a subtour. And the cost of it is, again, not more than the cost of the original tour because of how we set this number 14. And now we can complete this lift to a tour using our budget. Again, we use a recursive call to do this. Okay, so this will be a recursive call on just S. We add this, now it's a tour. Okay? If we can do it, we can pay for this completion with our budget, which we can. Then the whole thing together is an alpha times opt, and so recursively we have proved that doing this gives some alpha approximation. Awesome. So formally what we can prove is that if you have a row approximation algorithm on instances that don't have such nice reducible sets, then you can get an 8th row approximation for linearly weighted instances, and so for general placement. So we lose a factor of 8. Good. So we have seen a bit of this, and we have seen this reduction. Now, what do you do next in this chain? Okay. So what about instances that don't have reducible sets? Now you cannot make such progress anymore. Well, again, recall that the set was reducible if the contraction would decrease its LP value a lot. Okay, so here the sum of all these values was 17, and this removed and replaced by one vertex, which is, so let's say 16, and the 16 corresponds to the cost of the longest, shortest path inside. Okay? That means if this actually is such a low increase, let's say from 17 to just 16, then it means that there is a long path inside. We can actually find it efficiently because it's the shortest path between some pair of vertices. Okay? But clearly that is useful for solving a TSP. You know, your graph is almost Hamiltonian. Maybe, or at least each set that you have is such. Okay? So we will use this. Okay, so that's as much as I can tell you in this short time frame. For the rest of the story, well, come talk to me at the poster session. If you want to read the paper, there's a long version, but there's also a short version, which is just 2 pages, contains the main ideas. There are also several talks recorded on YouTube that you can watch. I recommend the poster watch. Okay, so for some summary, no problem. So again, our main result is that we give a constant factor approximation algorithm for ATSP. This with respect to the standard LP. Okay, so in the future, what we would like to see resolved is, people believe somehow that the right ratio is close to 2, or at least that it's not close to our constant, which is like 5,000. Okay. So we believe we can actually make this 5,000 a little bit better by making our proofs angular, but really still not anywhere close to 2. Okay, so we'll need some new ideas to get close to that lower bound. There is a nice problem called bottleneck ADSP, where instead of the tour that minimizes the sum of the weights, you want to minimize the maximum weight that you used. Okay, so now there is only a log n over log n approximation known. One other avenue to getting a constant factor would be through solving the thin tree conjecture. So that asks, given a held carp solution, is there a tree such that for any cut, this tree crosses this cut with only a constant factor more edges than the LP puts there? Okay? So if you could find such trees efficiently, then you would get a constant factor using a different method, and then that would also solve bottleneck ATSP. Okay? So that's also interesting in its own right. And for the bottleneck ATSP, because this implies that, so bottleneck ATSP is easier. So maybe this can be solved even though we can't make progress on the free trees. Okay, let's do that. Thank you.
We have a few minutes for questions.
I want to see all the posters in the poster session. Do you have a recommended ordering that I should follow? Is it ATSP or TSP? I don't know if the room is different.
No, but the poster itself is structured in a path. So if you want to follow, that's an easy one. Okay, yes?
What is the running time?
We did not compute the running time. It's polynomial, really. Yeah. So, okay, first we use the elliptic algorithm to solve the LP, and then we have to uncross it. That takes some time. Yeah, maybe single digits in the exponent, I would say. More questions?
All right, thank the speaker again, and we'll have